So hello guys, in today's video we will see how to calculate cooling load on a coil, or it's basically cooling load estimation. This method is used by the mechanical engineers to find the how much capacity of cooling coil should be there for particular room or area. For the selection of a air conditioning system for the particular room, the initially we have to find the cooling load or heating load on that room. So here we are having one example. We are having one room with a dimension of 8.36 by 8.47 meter, which is having four windows and one door, which is dimensions are given. For windows it is 2.3 by 1.3, and for door it is 2.48 by 1.48 meter. So these are the basic dimension. Now what mechanical engineer do here, or one particular server do here, so he will go and check the dimensions of a room initially, if there are sunroof or is there is open roof or walls, windows and door, all dimensions should be matched. And then he notice is there any other electronic devices such as speaker, sound, because they will dissipate their heat. So that heat should be also removed from the room. And how much capacity, what is capacity of that room, how much person or people sit there, that all data should be gathered and their total heat should be calculated before fitting the AC. So now here we can see dimensions of room we have taken. Now number of fans here are 4, number of lights are 8, its seating capacity is 77 people. Here we have taken one classroom, so 76 people student and one is teacher. So this is the classroom here. Now cooling load calculation means we have to calculate the load, heat load by the particular component or device. So first is indoor and outdoor condition we have to consider. Outdoor condition is 42 degrees Celsius DBT at 40% relative humidity. It's extreme hot condition of summer in this local, and its outdoor condition means what desired condition we want, that is indoor condition. It's 25 degrees Celsius DBT and 55% relative humidity, which is basic comfort zone of a human. Here, this is the important part of process to calculate the sensible heat gain from a room. So from what we get the sensible heat? Walls, windows, solar windows. Solar windows what means directly coming from the contact with the sun. So there will be heat gain also. And from the walls, windows, solar gain, we will get sensible heat. And there are some component like food, people. We will get sensible heat as well as latent. So we have to calculate particularly and separately. For the sensible heat from the room, we have to draw such chart, which is source. Now U is a overall heat transfer coefficient, A is the area, cross section area, equivalent temperature difference, S is a sensible heat gain. So UA delta T is here sensible heat gain. Here source we are having a northeast wall, southeast wall, northwest wall. These are the walls, roof and floor, door, windows are there. Two walls are there, so two different windows will be there. Southeast and northeast windows. Now solar heat gain from the windows. So yeah, well, the value of U we have to take from the standard data book, from the ASHRAE or other data book. We would refer ASHRAE more. Now A is the area, cross section area of that wall or door or window. Equivalent temperature difference we also have to take from the data. So what would be temperature difference? Means if there is one wall of 9 inches, so what would be temperature difference between outdoor and indoor? So that is temperature difference we have to take. So if we get all these values, so we have to calculate sensible heat gain, and then we have to add them all. So we'll get sensible heat gain from the room. So in this way we can calculate. So like this, we find such a chart in the ASHRAE book or data book. Here different type of windows are given, window glass are given. So for the particular window, we have to take value of U here 5.91, 5.7.24, 6.12. These are the given for the different type of windows. So center of glass, edge of glass is given. So it is a only glass type. So it is operable or it is fixed. So depending upon the application and the type of window, we have to take value. U factor. Once we get U factor, so it is chart for overall coefficient of heat transfer U for a wind velocity of 24 kilometer per hour. For the particular wall, we will get value of U from here. So what kind of wall you are having, so select it from here, and then you get value of U. Now sensible heat gain from a people. We are having 77 people in a room or capacity. So now here in this chart, we are having the rates of heat gain from occupant. Now it depend upon their activities. If whether they are seated, they are moving, or they are doing their work, or walking, or heavy work, or athletes. Depending upon them, their heat varies. So first category we have taken seated and very light work, which is for students. So now here we can see total heat for male and for female. It's different. For adult male, total heat is 130 watt, since where sensible heat is 70 watt and latent heat is 45 watt. So this we get from this from here we get the sensible heat and latent heat for the people. And second category is standing, light work or walking. This taken for the teacher. So sensible heat is 75 watt and latent heat is 55 watt. So here here we can multiply 70 by 76 and teacher 1 by 75. Here we get sensible heat is total 5395 watt and latent heat is 3475 watt. So and moving towards the next point, which is sensible heat gain from the infiltration. So first of all we have to know what is the infiltration. Infiltration is the unwanted air or extra air coming from the outside to the room, because here we are designing for the AC. So AC will transfer some air to the room, but apart from that air conditioning system, other source of air is there. Means from other source air is coming from the room, like crack window or opening the door. So air is coming. So ultimately it is increasing the temperature of a room. So it is ultimately increasing the load on a cooling coil. So that we have to take in the consideration before design. So basically we get here, we take one air change. Its unit is air change. So for the room, one wall exposed, one air change is taken. So from the one air change, we have to calculate into mass flow rate. So how we convert? V1 is equals to LWH multiplied by air change divided by 60. Here LWH is dimension of a room, AC is air change divided by 60. So we get volume flow rate into meter cube per minute. So if we put here value 1, we will get 4.189 meter cube per minute volume flow rate of infiltration. Now we have to calculate the sensible heat gain from the room. So we have in the previous lecture we have seen this formula 0.02044 multiplied by volume flow rate into temperature difference. From this formula we get the sensible heat gain 1455 watt by the infiltration. This is the heat gain by the infiltration. And we have to now calculate latent heat gain from the infiltration. For the latent heat, we have a formula 50 multiplied by volume flow rate multiplied by W1 minus W2. From this, we get a latent heat gain is 4942 watt. Now, sensible heat gain from the light and fan or electronic devices. Here, power we have taken is use factor. Use factor we have taken as 0.5. You can, if you are operating these objects or electronic components for the whole day, so you can take it as 1. If you are using it is for half a day, so you can take as 0.5. Now allowance is also added here 1.25. Now, then calculated the sensible heat gain from the fan, it's 200 watt, and heat gain from a light is 180 watt. Then sensible heat gain from the fresh air is if we are needing a fresh air also, so that will be add some sensible heat into room. Fresh air required from the child we have taken as 0.3 meter cube per minute per person. This much fresh air is required for a person, 0.3 meter cube per minute per person. So total air, fresh air we will require 77 multiplied by 0.3 is 23.1 meter cube per minute fresh air we require. Now OASH. What is OASH? It is outside air sensible heat. So we have to calculate outside air sensible heat and outside air light and heat separately. So we will get sensibilities as 8026.7 watt and latent heat as 5197 watt. Now moving further, room sensible heat and room latent heat. From the chart above, we have calculated the room sensible heat total. Now we have to add room sensible heat from a room, from a people, from infiltration and from the equipments. So we get total room sensible heat 21.765 kilowatt and room latent heat as 4.637 kilowatt. In the room latent heat, what we have added? In the room latent heat we have added from latent heat from gain from a people and latent heat gain from a infiltration. So now we are having a room sensible heat, room latent heat. From them we have to calculate grand sensible heat and grand latent heat. What is grand sensible heat? Grand sensible heat is basically room sensible heat plus outside air sensible heat, and grand latent heat is room sensible heat plus outside air latent heat. So we here get a grand sensible heat and grand latent heat. Now the mass supplied to the coil, here total heat upon heat removed. So here we get mass supplied at 1.88 kg per second, and hence uh, refrigeration load we can calculate mass multiplied by enthalpy change, we get into 30 into turn of refrigeration. Now how we have solved this? So we draw one schematic diagram. From outside we are getting air of 23.1 meter cube per minute fresh air, which is having dry bulb temperature of 42 degrees Celsius and 40% relative humidity, and the recirculated air is passing here. Now at the point number 3, mixing is takes place, and then mixed air is passed through coil. Then this cooled air is passed to the room. That is basic principle. Now using the psychrometric chart, we got the value of VS1 0.922 meter cube per kg. From this we get mass flow rate. So how to what are the steps? So first step is plot the point number 1 and 2 on the chart, indoor and outdoor condition, calculate the room sensible heat factor. We have calculated it. So room sensible heat and room latent heat we got from the chart and other data. So we get it room sensible heat factor is 0.82436. Draw that line 0.82436 line we have to draw from point number 2 or mixing point. So after the drawing, we get the mixing point. Here we are considered that there is 60% recirculated air is used. So four fraction is 4 by 6. TD3 minus TD2 upon TD1 minus TD3. Now we got the temperature at point number 3 is 31.8 degrees Celsius dBT. Condition of air before the mixing is 31.8 degrees Celsius dBT and 52% relative humidity. This point we got from a mixing. Now condition of air entering the room, which is at point number 4. Room total heat, we got M4 multiplied by H2 minus H4. From this formula we will get H4, and from this we get point number 4. So room total heat we are having 26.402 kilojoule per kg, and grand sensible heat factor also we are having 0.7514. So make the parallel line to the saturation line. Here you will get grand sensible heat factor line, and this is room sensible heat factor line. So in this way we can solve the numerical and get the value of total heating load or cooling load.